Good morning, my dear kids. In today's class, in the chapter electromagnetic induction, we are going to discuss the topic, the eddy currents. Is a mere theoretical. We don't have any exclusive numericals. So some 4-5 numericals I'll try to bring. After that, we'll go for the remaining time, some numericals on the motional EMF. Let me start the class. Okay, now. This is about the first we'll focus on the eddy currents. So the name itself, eddy currents, that one. So eddy means like unpredictable. The meaning of the eddy, that one, it's like some Greek or Latin word. Eddy means unpredictable here. Okay, let's get into some basics, this one. So let there be a conducting ring. Okay, we have a conducting ring. So this ring is having a radius A, will assume it. Here I'll make B bar directed into the plane of this conducting solid disk it is. Let this B bar vary with the time. So this iron disk, let me call it. Now, what conditions will arise here? Can you remember previous problem? I asked you about the power dissipation, everything. Just there, I asked you to neglect eddy current, but here eddy currents you have to take it. What is the basically conductor? Contains electrons, free electrons, and the free electrons, they can move randomly in any direction. And what about ions? Ions, they're immobile in conductor. They'll be binded by the bonds, and due to adjacent bonds open, the ions will not at all move that one, but they can vibrate above their mean position. But electrons, they can move randomly. No, there's a magnetic field is there. The electrons which is moving randomly will experience this magnetic field, that to time varying magnetic field. Then due to this time varying magnetic field, the electrons, they'll encounter an induced electric field. Due to that induced electric field, now the electrons starts moving. Now, how do the electrons they'll move? Will they have an ordered motion? The answer is no. So here what we notice is that these electrons, they will try to complete a closed path. Okay, what are these designs not designed? In this way, what happens, the free electrons which are present, they will complete a loop like this. They'll move in this direction. Means here the electron will be moving like this. Sir, why you are putting, okay, this is what? Path of electron. Okay, this one, I had to show it opposite, no? The induced current will be path of free electron. Path of free electrons in the disk. So why do they move like this? Because like you are, it will not be like in circular ring. They don't flow in one specific path here, very random. Like this individual electron, it will try to move in a circular path. What makes it to move like this? The induced electric field. We know if the magnetic field varies, there will be an induced electric field produced. Due to that induced electric field, these electrons will experience force. These electrons, E bar, okay, I think I'm path of free electrons, and the current will be in this direction. Okay, let me just put only this much. What is this arrow? Arrow indicates that the path of free electrons in the disk. Why do this one? Because you go back to the account to the Lenz law, the flux is negative. negative flux increases, d phi by dt negative, EMF induced positive. So the induced current should flow counterclockwise, opposite to direction of induced current, there should be electron. So what I'm showing is path of free electrons. These are called like eddy currents. These are called like eddy currents. Very difficult to predict any equations, that one. Now, whenever electron moves in some path, what will be that one? So it will encounter collisions with the ions, and thereby heat will be generated. They'll be drifting in this random path, better say. Rather than saying movement, these electrons will be drifting in this random circular path. Like that individual electron will try to move in this one. I think millions of electrons will be there, no? So like this, what you should do now, millions of this closed path is what you have to see. Will there be any heat generated? Yes, it should be. There will be heat generated. If you go and touch this, it will be hot. The temperature of this will continuously increase. From where it has come, what work you do to produce variable magnetic field, that energy is utilized to make these electrons to move in a curved path here. And due to flow of electrons inside a conductor in some random path here, heat will be generated. So that's why, like you see that one, we didn't brought anything, only one problem. Yesterday I brought it, that too what I said, neglect eddy current. But in fact, their eddy current will flow. So in the end, I wrote some instruction. So hardly we brought anything like a conducting surface here. Only everything will depend. We brought a conducting loop, conducting ring, triangular one, this one. That too, if a variable field is varying, we'll get this one. Means like a only variable magnetic field eddy currents will come. Okay, no, the answer is no. Okay, let's take the other examples. If I have a magnetic field, now let me take a plate. There's a plate. I'll start making it to move. Now the same plate now is going to enter. Now it is entering. I need more dots. This plate now, it is fully inside. Okay, this is about the situation is what I brought it. Okay, we'll analyze for this. What is this yellow color? It's a metallic plate. I'll write it copper plate. No, this plate starts. No, there's no magnetic field. There's a magnetic field is present. This one. This plate starts entering into magnetic field. Now it is entering. Now let me check it. Like anything will happen to its velocity. Now let's come for the Faraday's law. The direction of induced current is such that it should oppose its own cause. The direction of induced current is such that it should oppose its own cause. Now, in what direction the induced current should flow? In what direction that induced current flow here? No. Anybody? Sir, if it were a loop, we would have answered, but this is some conducting plate. So where is the question of any specific direction? At least let's use the Lenz law. Flux is magnetic field linking this is into the plane. So as it enters, the negative flux increases, d phi by dt negative, EMF induced positive. So therefore the induced current should be anticlockwise. Where to show that induced current? So can I draw it here? On the edges? No. An eddy current will flow. Here then eddy current starts flowing. Where? Only in this region. The moment where the magnetic flux is varying. In this region, no eddy current. The moment it enters, no, the entering region only. I have to show it entering, no, boundary. Yeah. This in entering region only, the induced, the eddy currents you have to show it, not everywhere. Okay, this was the magnetic field. Then we know this induced current. So definitely by Lenz law, the direction of induced current such that it should oppose the cause. Now you look at this, this tiny current carrying loops, shall we say they will behave like a magnet, electromagnet. And altogether, what they'll say, they will oppose this particular thing. So here, definitely this particular plate will experience a force F1. Now, no longer the velocity will be V, it will be V1. It got decreased because of retardation. According to the Lenz law, the direction of induced current is such that it should oppose the cause. What is the cause? The velocity with which the plate is entering into the magnetic field. So it should be opposed. How do it can oppose? By exerting a force. Okay, this force is due to this eddy current. So the plate will slightly undergo retardation. Now it has fully entered. Now, as it is entering, the eddy current will be there only in this region. Once the structure enters, there the magnetic field is constant. No longer eddy current will come. Now the flux linking will occur only at the point where, like at the point of a plate where it is entering. No. Now once it has entered, you can see no eddy current here. But sir, B bar is there. Yes, B bar is there. Flux linking is constant, so no eddy current. No, also no eddy current. Now again it starts living. So where eddy current will come only in this region. This is what you should not show eddy current everywhere here. Only in this region there will be eddy current. Now again, the direction of induced current is such that then finally it has entered into the magnetic field region with a velocity say like a V dash. Okay, it will remain V dash. Now again the velocity will change. Again decrease. So the direction of induced current is such that it should oppose the cause. Again retardation. Finally, this particular plate will move to the magnetic field with a decreasing velocity. No, here is what eddy current will come. You have to know, you should not show eddy current here. Where the flux linking varies. The moment the plate point starts moving out, there was a flux, now the flux has become zero. So suddenly what happened, there will be an induced current by Lenz law and an eddy current will flow. So you should not show current here in this way here. This will be wrong. Able to make it out? This one. So what this eddy current now? So in fact, they'll exert a force. Can we calculate this? Not possible. Of course, we have equations, but at our level, not possible to predict anything like a force something. They may make a problem. The eddy current will exert a force of say 10 Newton. If you increase speed, then this force will increase. Okay, the eddy currents will come only, not like something time varying field only will produce electric field, will produce eddy currents. No, when a loop enters a magnetic field or when it's leaving magnetic field, so here, when a conducting plate entering or leaving the magnetic field, their eddy currents will come. Where the eddy currents will come? Only at the interface. This one. The part of plate which is at interface, there only eddy currents will come. no eddy currents here. No eddy currents. Why no eddy current? There's no Mansfield linking. Why, though Mansfield is linking, why there is no eddy current? Because flux linking the plate is constant here. So I have to write here no eddy currents. Where do eddy currents are produced? Eddy currents are produced. Let's give explanation. Hope are you getting? It's a very small theoretical idea, but it's having wide applications. I'll explain the applications also. You'll be surprised what is use of basic science and the engineering applications, how good they are for society. I'll give examples at the end of this. Now, eddy currents are generated in plate when plate is entering or leaving magnetic field region. Then in the plate where it will be only the at the boundary. Eddy currents not at all over the plate. Only a part of the plate which is at the boundary, there only eddy currents are produced here. No eddy currents are present I'll pull it up. Eddy currents are present in plate. In a plate. Eddy currents where a part of plate is, where a region of plate is at interface or at boundary. What is a boundary? This is a boundary. Yeah? This part is a boundary. Where a region of plate is at boundary of magnetic field. This part is very important. In the whole plate, eddy currents are there? No, only a part of region of plate which is at the boundary of the magnetic field. There only the eddy currents are produced. I think these are the two very important points which I'm trying to stress here. This eddy current, what they do? They will retard. That's all. Due to eddy current, the plate will undergo retarding motion. One more last point. Due to eddy currents, the plate undergo retarding motion. These are the three primary things is what I studied. Anybody having doubt, you can clarify. Okay, now let's take this one. So when I was studying, I think this was like a dream come true, like something. Now we have in our home induction stove. Hope everyone induction stove. Usually be black color, no? It will be. All of you seen induction stove? This will be more safe, no? It is like even if you put your arm there, no? Induction stove. The induction stove is nothing but the application of eddy current. Nothing big will be there. So what we do is like, we have to, this is ceramic surface. This one, base of frying pan. So then what they do is like, what they ask is like a induction, like a cooker. The bottom part is very important. I'll draw the free body diagram. It'll be easy for you. This is the bottom part of the pan. Let's bring all the structures. This is a ceramic layer. Here I'll bring a solenoid. There's a signal. The signal is a variable one. You can see this as a function of time. A varying signal is what? No, this is a solenoid. This structure is a solenoid. Everyone knows solenoid. What it does, it will produce a magnetic field. This is the, I'm drawing free body diagram because most of you find very difficult like this a physical one. And this is the ceramic, just only for our protection. Ceramic surface. You can also sit on this induction stove. So this is the bottom of that particular cooking pan. This will be made up of usually bottom of cooking vessel. Even if you want, okay, you can. Yeah. So this is the bottom of like a bottom of cooking vessel made up of copper. This is something very important. Okay, this can be steel upper part. I'll bring the copper color. Okay, no. So you can see this will be the basic structure of the thing. Now let's come for this one. When I send a varying current here, there's a definitely varying current here, no? How do? By emotional EMF I can produce it. In general, in house, this will be the current that is available. If a current flows here, so go for how the magnetic lines of force. The magnetic lines of force will be I'll show only two lines. Diagram again will be, looks very odd. Yeah. So what are these? These are the lines of force. Everyone knows this. So here the direction of B bar, you can put it here in this way. This will be the some current. No, when a varying current flows through a solenoid. So what this solenoid will do? Definitely this solenoid will produce a varying magnetic field. And look at this B bar. So resultant B bar, I'll just show it in this direction. What is B equal to? Mu naught Ni. In fact, I is equal to I naught sine omega. What do we expect B bar? B bar is going to vary with time. This was that expression for I. No, B equal to mu naught Ni. So definitely you can expect I naught sine omega t. Now this is a bottom of cooking vessel made up of copper. I think this is something very important. The last end I put it a comment. Let everything with the same color. Cooking vessel made up of copper. I'll write here copper. No, just now we studied, no, a varying magnetic field will links the conductor and eddy current will be generated here. And we know that if a current flows in a conductor, there must be generated. So it will be generated. Now, what all you have here, cooking substance. So what that cooking substance now? It will start getting boiled. These are not eddy current. Huh? These are not eddy current. So this is the what we have the I think I'll make it some other color. Very simple, no? So can be asked in advance. So many, I think twice, 3 times they've asked. So any of questions of like this also they may bring here. This is the I kept rice to boil. I'm vegetarian. I'll go for vegetarian food only. Okay, there's a rice. Rice granules that we have kept for boiling. No. So what this particular no? So I'll send a varying current. The current flows through a solenoid. The magnetic field will vary, and the varying magnetic field will link the base of a copper. And we know from there eddy currents are generated. Due to this eddy current, it will be generated. It will be absorbed by this water and rice which is present, and the water starts boiling. The rice granules will absorb it from that and get boiled. And I'm going to able to cook the rice here. Now, okay, by chance, I'll touch this ceramic. Anything will happen to me? Nothing. You can sit here. You switch on and you sit here. Nothing will happen. Only magnetic field will link your hips. That's all. If you instead of this vessel, you sit here. So the magnetic field will link your buttocks. Nothing will happen to you. Anyway, like we are not made up of water. To some extent, after 10, 15, 20 minutes also, nothing will happen to it. You can't sit inside this container because the copper will burn you. It's so safe that you go and keep your arm. You remove this vessel, switch on this, keep your arm, nothing will happen to you. Only thing is only thing is like a magnetic field, varying magnetic field, when it links the bottom of this induction cooker or induction this vessel, no, then only what it will be generated. Nowadays we have why only we go for copper, because there it's having less conductivity. Means there the magnetic field flux linking it will be more and more it will be generated. You can go for steel also. You can keep nowadays, even some induction cookers have come where you need not to go for specific. You can just keep any steel one also. Yes, it will work out, but the power consumption will be more. Power consumption will be more. Nitesh, DC current, what is the DC current? Constant. If I constant, B constant, if B constant, no magnetic flux linking. Magnetic flux will be there. Magnetic flux will not vary, no eddy current. Simple idea here. So got this. I think this is something. No, I think this is the some European student. He got an idea. Some long back, some 60 years back, he got an idea. Why can't we use this eddy currents for cooking? That one, he proposed it. Later, what happened after 2005, what happened? We are able to have this one. When I studied, I think this diagram were not there, to be frank. And I never heard also induction cooker. In 1990s, I was there in the class 11, class 12. I never only eddy currents, yes. But we never had this diagram, this equipment itself. But it was only proposed by one of the student in European student. No, what happened? He was studying in the BTech engineering. He just proposed, why can't we use this eddy current? He made a project, and that project, what happened? Later, the industries took that and they started manufacturing. I think this will be a future of cooking. You know that slowly we are migrating from LPG. How eddy currents random? No, yeah. Use some brain. Huh? There's a bottom. At the bottom, what happened there? Eddy current will flow. So we are not bothered. No, how this electrons will flow. Is it any use? You want to cook rice and you want to eat rice. So will you bother about like anything here? Only it should be generated. That's all. No, here eddy current will flow. At the bottom, eddy currents will flow there. So due to the flow of eddy currents, it will be generated. Eddy currents, what will happen? It will be again each individual electron you can predict path. That's all. But the eddy currents here, they'll flow like this. This one, I think it's one of the beautiful innovations, what we can feel, what eddy current. To be frank, when I was studying also, we didn't have like this induction cooker something. I think slowly people are accepting. People are thinking that you'll get a shock. Why you'll get a shock? You tell me. Where is the question of shock? Where is the question of shocking, electric shocking? Nothing is there, no. Even if this spills out, nothing will happen. It's a ceramic. I think you know ceramic, but it will permit the magnetic lines. That one. So where is the shock? I think this will be covered inside the cooker, inside that stove. This will be totally covered, and that will take less space. I think you do one thing. Induction cooker, those who are not aware of physical world, just at least watch it in internet. Induction cooker, that particular thing, so many things are there, and it is more efficient. Based on this current, it's alternating, doesn't matter. It's alternating current, positive, negative, doesn't matter. Please use some common sense. Any one specific direction I can put it, because even the direction of B bar also will vary, will not be always upward. It's alternating current. Positive cycle, current will flow in one direction. Negative cycle, current will flow in opposite direction. Don't bother about that. Okay. Yeah. So it's I think just very simple. It's a cost effective also. You can produce this in home. You can produce this in home. You can produce this in home. Within around 800 rupees, you can have this induction cooker. Solely, and you can control all the things. You see the induction cooker, no? You can control the temperature, you can control the heat, and to what time it is. I think LPG, it's not possible. We can't control it. But induction cooker, I can control the amount of current. The amount of current will decide what amount of heat should be generated, what temperature should be generated, for what time only current will flow. I can control that. So induction cooker, what will happen is some sort of like a programmable fuel. You can, it's efficient also. LPG cylinder and induction cooker. I can say that induction cooker is, induction stove is more efficient than other thing. But of course, in India, I don't know, like we are not giving priority for this. This is the more beneficial. Just for 10 minutes, the milk should get boiled. Only for 10 minutes, it will get boiled. For what temperature? Decide temperature. Finish. Show. You can save the fuel like anything here. Fuel in this sense, the current only. Okay, this is a best application of the eddy current.
Sir, I have a doubt, sir.
What doubt?
Sir, in the left image, in the frying pan, they have assigned a direction to that eddy current, sir.
It's a, why don't you use some common sense? This current I will flow, will it flow in one direction during positive half cycle, one direction?
The left side image, sir.
Eddy currents are there, yeah.
Yes, sir. That direction, how it is assigned, sir, because it is random.
My dear, this eddy current will flow in some. I shown no. What is this? Why is I didn't show your arrow?
Okay, sir. Yes, sir.
Please do think. Put effort. You have to put some effort. Are you not seeing your arrow? Why this arrow like this? But by Lenz law, the same thing here. But here, you mean to say that eddy currents are here, not here or not somewhere in air. That's why you wanted to show that one. Now, what is this? There's a based on the Lenz law convention. So here, if you want, I can show it here. Okay.
Yes,
This
sir.
one.
Understood.
Yeah. And now something like this, a conducting disk. I'll give angular velocity omega naught and I'll release it. What can happen to this angular velocity? And what I do is, this is the axis of rotation. This axis of rotation. Then there's a magnetic field is present here. No, I'll give angular velocity. Anything will happen to this conducting disk. Conducting disk given angular velocity. Can you say anything about what can happen to its angular velocity? So here this magnetic field is there, which will produce magnetic field. Now, okay, you look at this one. This part of the structure, there's no magnetic field. No, the moment it enters here, the moment it enters here, it will encounter magnetic field. So suddenly flux is non-zero. So flux linking that region is varying. So an eddy currents will be produced. Flux linking the changes. According to Faraday, so EMF will be induced. Then induced current should flow. But as there is a conductor, and eddy currents will flow here. These eddy currents again, according to Lenz, the direction of induced current is such that it should oppose the cause. So what they do, they'll produce a retarding torque here. This is due to what? Due to eddy currents. That's due to Lenz law. So what do you expect? The disk, when you give angular velocity and release, it's going to undergo retarding motion and finally comes to rest. From where that retarding torque has come? Due to the eddy current. So can I bring this eddy current to produce retardation? Yes, electromagnetic brake will call. Electromagnetic brake. This is used in braking systems. If a body is rotating, what is the advantage of this is like, I can stop it by applying tangential force. What is the problem? Machines know how to stop something rotating. If you apply some force here, definitely the surface of this what will happen gradually, it will get damaged. That one I can bring is, I think if you go for a cycle, there's some brushes will be there, no, for a rim. If there's a rim, a brushes will come black color one, a brushes will come here. So why do we bring it? To put brakes. But if you see the brushes after 6 months, we have to replace, no, anything happen? Yes, they'll get damaged here. The same thing in a rotating machines. If you want to stop it, what is the biggest problem? Like another body should come in contact and friction will come. Due to friction, the surface will happen gradually, its thickness will decrease or the diameter, anything will happen here. So how to stop it without touching it? I'll bring eddy currents. This is the best simple method. I'll bring this electromagnetic into picture. This magnetic field I produce it. This magnetic field will see that a retarding torque is produced. Due to retarding torque, it will come to rest here. So these eddy currents are widely used as a electromagnetic brakes, where I can now the disk is not in contact with any other surface. If any other surface comes in contact, we'll see the things that will happen to the brush and the rim and the brush in the cycle. You might have seen this one. So gradually this particular thickness of this brush will decrease. So therefore, there's a condition here. So when you give angular velocity to the disk and release, it's going to describe a retarding motion. So here we'll write the equation here. The disk is given angular velocity and released. Then due to flux linking the flux linking the region of disk. Varying with the time. Eddy currents are produced. The direction of induced eddy current, the direction of induced eddy currents are such that they generate retarding torque on the disk. Sir, can you show eddy current, sir, please? Okay, well, I'll show it, no problem. Yeah, this color. So here only in this region. So here, look at the Mank field. So it will enter here, no? So that the eddy currents of flux, negative flux increases, d phi by t negative, EMF induced positive. So the direction of eddy current should be like this. Everyone? Okay, fine. This one. Now, look at the eddy currents. There are two things are there. In this region, eddy current should be in this direction. I can't show many. I'll show only few. What about here, eddy current direction? Anybody wants to answer? Will it be same at both the regions? Should be clockwise here, no? That should be anti-clockwise. Any reason for that? Any reason for that? Here, the flux, negative flux increasing, d phi by t negative, EMF induced positive. The induced current should flow anti-clockwise. Here, the negative flux is negative. Negative flux decreases, d phi by dt positive, EMF induced negative. The induced current should flow clockwise here. So there's a direction of eddy current. So direction of eddy current at P1, P2 will do marking. There's a point P1. There's a point P2. So what is the direction of induced current at point P1 and P2? Will be different. Getting no? So at P1, it's not a mere diagram. In all the internet, when you see diagram, now you know concept, you should analyze, but students are just downloading and seeing, okay, there's eddy current. Who will analyze? Who will analyze? You see every diagram, you can give explanation. So much, one page, you can write it. At point P1, flux is negative. d phi by dt, negative. EMF induced, positive. So eddy currents flow zooming, what all we write. Okay, I think, yeah. Now clear. Is it visible? Okay, no, I think this is the maximum possible. Now you can see this eddy currents flow in counterclockwise. No, flux negative at P2, sorry, at P2. Flux negative d phi by dt, positive, EMF induced, negative. So eddy current flows in clockwise loops. So they may ask you the questions of these kind, you should be very careful. Not mere diagram. In the diagram, they will ask you to analyze. And the direction of induced, how to get the direction of eddy currents? Again, the same Lenz law. Please hope everyone is able to understand how to predict the direction of eddy currents. It should be due to Lenz. So how to stop a rotating object? This is the one best method what we have. No, advantage we have seen. The disadvantage of eddy current. The eddy currents, again, they are unwanted things in some of the applications. At any cost, they should be minimized. If you don't minimize, it's a big loss in that application. So what we are discussing advantage, no? At the same time, in some of the applications, at any cost, they should be minimized. If you don't minimize them, then gone. A good example is transformer. So when we study in the AC circuit transformer next week, no, then there I'll introduce that eddy currents. Now time being, I'll try to avoid. Now one more application. This you must be ready to predict the direction of induced current. This is very important. Eddy currents direction. Here also, let me go back. I'll show at least one. So what do you expect the direction of eddy current here? Like this. One at least I'll show it. Okay, agreed. This one. No, one more application. Suppose say if you send a let me have water. In some applications, suppose induction stove, we need eddy currents concept. In some of the applications, the eddy currents is a big headache and they have to be overcome. So how to minimize that effects of eddy current, that we are going to see. Now, suppose if a current flows along the surface, I think there are many problems you might have seen. There's a conductor. There's a conductor, cylinder, cylindrical rod, where the current will flow on the surface. On the surface. So you know, this will be like a solenoid, no? This is current here is entering and current here it is coming outside. So what do you expect the man field? Somewhere like this. And I'm using for some application this is. Then what is the biggest problem is like here the eddy currents are generated because if a variable current, if I send it, the man field here will be varying. This is similar to solenoid. Are you able to understand? Eddy currents can flow freely inside this structure, where the structure here inside here. Now, what is the biggest problem is like, yeah, this current here it is entering, it's leaving, similar to solenoid, so it will produce a magnetic field. Let's assume. Now, this magnetic field will pass through this structure, no? As there's a varying current, a varying magnetic field is produced. A varying magnetic field will link inside everywhere the structure. Then, according to Lenz law, if this current I is increasing, so definitely what do we expect here? Suppose here B bar will be out of the plane. B bar will be out of the plane. So these are the directions of lines of force. So if you stand here, the B bar will come like this. Then if you, what is the flux? If I is variable, the current which is flowing is variable. Then, so what is the flux? Flux is positive. You are standing here. Flux is positive. d phi by dt positive. EMF induced negative. So how the induced currents? The eddy currents now they are going to flow everywhere inside the metal, not only on the surface, everywhere inside the material. I'll show only few. The diagram is very small. So this will be the direction of eddy current. And what these eddy currents, they will generate heat, and this is not needed. Which is not at all needed here. Now, how to minimize this eddy currents? How to minimize this eddy current? So what I do is like the same current, the current which is flowing, I will send it here. It will produce a magnetic field. This same cylindrical conductor, I'll make it up with thin wires. Are you able to see the diagram? The same, instead of solid cylindrical rod, I'll make this cylindrical rod with a thin wires. I'll club them all, then we'll get a cylindrical rod. Then, okay, I'll send a varying current. As a magnetic field will be varying. Here also I'll get a magnetic field. Here also I'll get a magnetic field. Now this magnetic field is varying with the time. Then what about eddy currents? This structures will not permit. I'll show only this surface. It'll be easier for you. Okay, now the eddy currents here will be now instead of this, I'm constructing this structure by a pipes. Okay, few pipes I'll show it. I can't draw so many. Like this cylindrical wire rod, it's made up of a wires here. These wires, what they do, they're very thin actually. They're very small so that the eddy currents cannot complete a loop. And individual between the things and insulating material will be applied. No, this is the thing. Now here also eddy current wants to flow. The eddy current wants to flow again, it cannot complete the loop, no? It cannot complete the loop. The reason for that, if you take one material, so what I do is like there's a thin wires. This is cylindrical rod. This is like a cylindrical thin wire. Now each wire, what we do is like there's a wire surrounding it. I'll give a coating, insulating coating, small thin layer. No, this is the metal wire, cylindrical rod, cylindrical copper rod, cylindrical thin copper wire. This is a copper wire. Surrounding it, I'll give a coating, insulating coating. Now, what this insulating coating will do? Will it permit the current to flow? Now, for everything, what happened? The insulating coating will be given. I'll show it here. So what this insulating coating will do, will not permit the continuity of eddy current. So to some extent, we have minimized the eddy current by almost 80%. Are you getting? No? So in some applications, I have to do like this. There's no other way. Problem solved. Here the eddy currents are minimized here. Eddy currents often will not get a continuity of path to flow. But sir, it can flow in this region. I'm showing big diagram, use common sense. Look at here. Thin wires, thread. So the eddy currents, what happen, will not get a path to have a closed, will not have a region to have a closed path. Finish over that one. So the eddy currents are, we should not say eliminated, or minimized here. So these are the eddy currents. Here eddy currents are minimized. What we are doing, we are not permitting eddy current. We are not giving a space for eddy current to complete a path. That's all. Nothing big we are doing here. Like that, the same cylindrical rod, now I can, if I construct with a wires, and that to each wire, if I provide insulating coating, I can minimize eddy current. I don't want eddy current. Please do understand here. Induction stove, I need eddy current. No, I don't want eddy current. In braking system, I need eddy current. No, it can be like this even for a rod. Suppose say this, instead of this, if I have a rod, it is possible, but what is the thickness of wire? Use some common sense. Look at the diagram. Thickness of wire is so small that the eddy current, even in this wire, will flow. That will be minimum. Not making observation of diagrams. You see, so thin they have shown. No, it is like this. So here there's a structure where there's a magnetic field is linking it. No. So here the magnetic field is there. The magnetic field is directed in such a way that it will be into the plane. Now, because of this, there will be an eddy currents here. I think now use some common sense. Now, instead of the same structure, if I make it with a I'll stack thin plates one upon the other. Can I bring this? Can I produce this rod of this shape? No, again, B bar is present. B bar is varying B bar. B bar varies with the time. And what is this? This is a rectangular rod. But what I made, I sliced it up. No, I think all of you know, like a paper in notebook, how you have one. I'll take a one sheet, then I'll put stack upon one. Again, what we do is like a, between the sheets, what we do is like a, if this is the sheet. Between the sheets, I will bring an insulating layer. It's a, like a, I'll take a thin iron sheet. I'll apply with a brush, I'll apply insulating layer. I think bread jam. Okay, there's a bread, one slice of bread. Then I'll apply jam. That jam is the insulating one. I'll put another slice like that. The bread what happen will be one piece will be kept on other slice. In between jam will be there. The jam will not permit. It's insulating. Bread is a conducting. Let's assume that one. Now any eddy current is there. It has to. It is not having a path. We are not providing path to complete the loop. Sir, can it flow in this gap? I'm telling it's a thin millimeter. Eddy current here. It was huge amount of power loss. it is minimized by almost 99%. Sir, why can't it flow in this small gap? I'm telling this is a millimeter thickness of one sheet. In that small thickness, the eddy currents which are flowing will be minimized to almost 99.9%. That 1% I'm not bothered. So here the eddy currents are not permitted to complete the loop. Okay, this what you have to think here, like this is the copper rectangular copper rod. Here, what is this? Rectangular rod made up of thin copper sheets. Then there's a copper. The green color is an insulator. So we are not permitting, the eddy currents are not permitted. Eddy currents are not permitted to complete the loop. We are minimizing it. We are minimizing it. So like this, in the applications we need, though the magnetic field is varying, still no eddy current. Eddy currents are minimized here. Okay, depending upon the application, you can see here. Like this, we have plenty of, at some applications, at any cost, I should minimize eddy current. In some applications, I need eddy currents. Please do understand. So these are several methods we have brought it. Okay, let's go for few more like. Now, same thing, the plate, there's a uniform magnetic field is there. And I want to minimize the no, this is the plate I'm bringing. Like a comb, all of you, comb, metal comb, let's assume that one. And there's a uniform magnetic field is there. B is uniform, directed into the plane. Now this particular sheet is what, like a, there's a iron. I'll slice it up like this. Now I'm going to move it. Okay, now can you, I will just color it so that it'll be, you can notice that. You can exactly notice that we have removed some sections of iron there. Oh, no. Comb. I think best thing, metal comb. Now, what is this? This like a metal comb. If I move this metal comb in this magnetic field, then we have iron plate, and the same thing. Let me bring another iron plate. Let's see that in both the cases. What about the eddy current? Yeah, we have. Let's go to our diagram. Now eddy currents will flow, but it'll be less compared to the previous one. So here the same metal plate, I'll bring it. The similar metal plate, I brought it here. No, there's a plate 1, plate 2. Both are given velocity, both are given velocity. In which case, there'll be eddy currents here. Where eddy current in this region. Will it be eddy currents will flow in all the regions? No, only the region where the magnetic, the at interface only it will be there. Okay, no, there's also iron sheet. Why there are no eddy currents? We are not permitting them to continue the closed path. Similar to comb. Not seen comb, please, you are at home, make observation and come. But tell me, like, in which case the retarding force will be more. Here, no, in second case, the retarding force will be more. Here, the retarding force will be less. F1 will be less than F2. The reason for that, less amount of eddy current will flow here. Here, the eddy current will be flowing is maximum. Eddy current will flow in this small region, but it will be negligible, no? Almost maximum we are minimized by 90% by slicing this particular plate here. So in some applications, I should minimize eddy current. I've shown several examples. Here also this thing. A plate which is moving through a magnetic field, where it is entering magnetic field, eddy current effect should be minimized. So I'll slice it. The iron sheet 1, iron sheet 2. Similarly, when it is living also the same condition. So where all eddy currents are needed, okay, I'll try my maximum level to produce eddy currents. In where all eddy currents are to be minimized, I'll try my maximum level to minimize them. Hope everyone is able to understand. I think this is a very good versatile theoretical things. You don't get numericals, but any of examples may come rotating, translating that one. So in iron sheet 1, so what we do is by slicing, slicing the plate, we are not permitting eddy currents to complete closed path. So in iron sheet 1, in iron sheet 2, the eddy currents, not permitting the eddy currents to complete closed path, so eddy currents are minimized. Hence, less retarding force. The eddy currents are free to flow. Hence, more retarding force. But where eddy currents will flow, only the region where at the interface, not everywhere here. Getting, so you may encounter, so I'll just notice down. I'll once again, the last will conclude here. Few more applications we'll try. I think that the same set of diagram. So some are getting confusion. Let's take this example. There's a magnetic field region is there, where eddy currents, the primary thing, will give this numbering of plate. 1, 2, 3. Where eddy currents at 1, 2, or 3. One is already into the plate, into the magnetic field. No? What about three? Three lies outside the magnetic field. And what about two? Two is at interface. At region 2, there'll be eddy current, not at 1, 3. No eddy currents at points 1 and 3. Eddy currents flow regional, right? It better. Eddy currents flow at region 1, 3 it is. I think this is again very important, not throughout the plate, only the region of plate where the magnetic field suddenly either increases or decreases. There only the eddy current will flow. Now, several examples can be asked for you. You have to be very careful here. So this is the inclined plane. Then there is a magnetic field region. Then I will release a plate. Or this is a block or anything, what will be that? What will be its acceleration when it is passing through this magnetic field region? It's a conducting block. Iron block, I'll write it. There's a gravity is present. There's a magnetic field region. I'll delete it from rest. So this, let me put it, iron block. No. Anything can you say about the acceleration at point P1 or when it's fully inside? I think there are several ways of asking some questions. That's what I feel. Huh? Let's complete it now. What will be the acceleration when it is entering and leaving? Very tricky questions related to mechanics can also be brought. Let's go for when it is entering. Anything will happen. Will act, inward action mg sin theta will act in this direction. Then will there be any eddy current as a retarding force? F AD, I'll write it. So definitely it will have acceleration. This acceleration will be less than g sin theta. Again, when block is leaving magnetic field, again there'll be eddy current, the force due to eddy current. What will be the acceleration? Okay, now let's come for the let's come for, it is entering. So the direction of induced current is such that it should oppose the cause. What is the cause? It is entering. So it will oppose here. Now it is leaving. Again, the direction of induced current such that it should oppose the cause. It is leaving. Again, it is leaving means it should oppose upward only. The eddy current force will be again, it will be upward only. more troublesome because we don't have any very big good formulas to justify all these things. A student must use the basic knowledge and it should justify all these answers when it is living. How the mg sin theta will be down the incline. Again, eddy current force will act up the incline. What is the acceleration? A2. Again, this A2 will be less than g sin theta. Just be careful. So anything of this kind will be asked for you. And check the mains paper, advanced paper. They just mere theoretical information, but they preferred this equal weightage, induced electric field, eddy current. Both are given equal priority. Now let's some. I have a magnetic field region. Okay, this one more question. Let me discuss. This is solenoid. I'll send a current I. Now here is a conducting disk. And it is suspended. Just nearby, it is placed at the mouth of the nearby mouth of the solenoid. Okay, I think you have to really get this one. So there's an iron disc. The resistance of disk will be very small. So I'm going to send a varying current. Okay, I'll switch on the current where the current is I naught T. Now, what will happen to the disk? So when current to the solenoid or I'll bring like a switch. It'll be much easier. Such that this current is a varying current. So I'm going to close the switch. So when I close switch, a varying current will flow. Then just after closing switch, what will happen to the disk? Gravity is present. This having a mass m. This will have a small resistance. This is a solenoid. Just after closing the switch, what will happen to the disk moment? What will happen to the disk moment? No. I want answer from your side. The disk, will it move towards solenoid, away from solenoid, or the disk will rotate, or the disk will remain? It experiences repulsive force. Yashovardhan. Okay, one answer I got it. Moves towards solenoid. Gayatri. Contradictory answers, both of you. Think once again, both of you. I think both contradicting who is right, who is wrong. I think better to analyze once again. So we'll do one thing. We'll go back to our basics here. How the magnetic field produced by this moves away from solenoid. Nitesh. Okay, I'll do one thing. I'll stand here. Then what is the magnetic field produced? The magnetic field produced by this solenoid will be in this direction. I think that there's a primary thing which we must have the idea. I don't want to show all the lines of force, just I'll show it. This is a B bar produced by the solenoid. And so according to this person, the flux linkage will be out of the plane. See, I don't know what's happening. Students, they just look at diagram and they want to answer. They don't want to analyze here. It's a solenoid, you have B bar, then there's a person is there. So this person will see that this magnetic field will also link this disk. So positive flux. And what is the type of current? Increasing current. So the B bar should also increase. If current increases, the magnetic field will also increase. So positive flux increases, d phi by dt positive. EMF induced negative. EMF induced negative. Here in this, and induced EMF is negative. Then negative means again, it should flow clockwise. Then we know this will be like a bar magnet, no? The solenoid will be like a bar magnet. And dipole momentum of this, if a current is flowing, so how the dipole moment descent should be the north pole, this should be south pole. And here the current in this will flow clockwise. Then how M bar of the disk will be in this direction. The dipole momentum of solenoid and the dipole momentum of ring, they are like this. So descent will be south, north, south, south. There'll be repulsive force. So it will experience a repulsive force. So induced current here will be negative. That eddy current carrying loops will each electron will wave like a magnet. The resultant magnetic field, magnetic momentum of the ring will be towards right. So in eddy, in this disk, you can show it if you want. You can show the eddy current. So how the eddy currents will be? They must flow in clockwise. Each eddy current now, each electron will be like a tiny magnet. The resultant magnetic field of the ring will be due to individual electron. I think we must analyze here, not like something seeing and predicting. Please be careful. Already they have asked such things in advanced exam. Again, they may trouble you. Let me go for one oscillating pendulum one. This is a north pole. Okay, these are the bar magnets. Here I do have a string. And there's a metal plate. I'm going to release this metal plate in this, and it's going to swing between the poles. I think 3D diagram not possible because 2 bar magnets we have to show it. Okay, I'm able to get one thing. Okay, I'll go for plane diagram. And the plane diagram, so the magnetic field, if I show the north pole down, no, so the magnetic field region, okay, there's a plate suspended. Okay, I'll help you with plane diagram. Yeah. The magnetic field region is this one. Whole to release it. And there's a very favorite question. It's there in most of the books also. There's a string. There's a iron plate. The same B bar is what I'm showing it. Okay, it should be out of the plane, no? Well, I'll do one thing. So many north will make this south. I think this will be justified. Now, as this plate enters, as it swings, anything will happen to the plate. What type of oscillations is going to describe? I'll release from this portion. So it starts swinging. It starts swinging like this, no? So the moment it enters here, eddy current will flow. The eddy current will oppose a retarding torque. And because of that, the angular velocity of this decreases. Then again, when it's leaving, again, retarding torque will act here. So all together, so what are the oscillations of this plate? Damped oscillations. It's going to describe the damped oscillations here. Here, the plate will come in such a way that it will move normal to the magnetic field. 2 ways I can make this plate to move. Here is what I'm showing the diagram. The plate will come in such a way that it will cut the lines of force. Here you can see this. The lines of force are into the plane. The plate will enter. So when it is entering, this part will see. I think we can draw a straight line. It looks good. Now, when it is entering, we'll see the situation. Any eddy currents will you bring into picture? Yes, there'll be eddy currents, no? So where we have to show eddy current? Eddy current we have to show in this region only. And due to that, there'll be retarding force. Gravity is present. Then a retarding torque is set up by the eddy current. So again, the same plate, when it is living here, will there be any return? Will there be any? It will have velocity in this direction. Don't show horizontal. So they say v1. So again here it will have velocity perpendicular to that string. No? v2. So the eddy current should act here in this direction. So what this eddy current will oppose this one. So what do we expect the oscillation of this plate is going to describe a damped oscillations. The plate is the iron plate. Will describe now, if you slice it, if you make it like a comb here, then the damping effect will be minimized. Are you getting? Like a comb, if you make it, slice it here, then here also you slice it. Now, it will describe, but it will become underdamped. Can you remember damped oscillations? We have undamped, damped, overdamped, critically damped, and underdamped here. Critically damped means this is what happens here. Overdamping means it will take a lot of time. If you do slicing here, yes, the plate will swing, but for every oscillation, the energy will decrease, but the decrease in energy will be very less. So gradually the amplitude of oscillations decreases. So how you do slicing, that will determine what type of oscillations it is. Hope everyone is able to understand. I wanted to just clear. So when it is entering or leaving, there will be an eddy currents. The iron plate will describe damped oscillations. And finally, what will happen? It will come to rest in somewhere in the magnetic field with the string vertical. Now, provided here, like how the plate will swing such that it will intersect the lines of force. So can I make it to oscillate in this way? The same situation. So let the lines of force be I think I can't. Oh, B bar will be tangential to the plane of plate. Such a way that the B bar will be tangential to the Now I'll finish off this diagram, little bit some. Yeah. Now you can see this. There's a plate we have here. It is suspended here. Now how B bar is directed tangential to the plate and strict condition. Here what B bar, here the plate will intersect. In this case, the plate. See this, the plate intersects the lines of force, the magnetic lines of force. Here, what about here? The B tangential to the plate. Here, the lines of the magnetic lines of force. Connected tangential to the plane of plate. So there's a B bar. produced by Ohm by the same thing. So what about your eddy currents? Anybody wants to answer? Second situation. I can release in such a way that the plate can swing in such a way that the B bar anybody here? Eddy currents, undamped oscillations, nothing, no eddy currents here. Flux linking itself is zero, no? Flux linking plate is zero. Matters a lot. How it swings matters a lot. Flux linking. Plate is zero. So no eddy currents. No eddy currents here. That one. No eddy current means definitely the plate describes undamped oscillations. If you slice it as to some extent, you can minimize the damping effect. So how you slice it, that will determine the nature of damping effect. I think that it's a unlimited, the way the topic can be, they can pull you to this any extent. You should be very careful. If you check the advanced mains paper, all theoretical questions only will come. You should be extra alert, that's all, eddy currents. But it's very important. I'm telling this one, you check the advanced mains papers, you have plenty of questions on this very small, tiny topic. So such topics, if you revise and go to the exams, and if anything comes on safer side. Okay, well, so this is about, so try to think on other numericals which are there in the mains advanced papers. So things will get balanced for you. Very less number of questions are there. So I gave a lot of diagrams, at least some nature of questions. Even we don't have any questions on rotating one. Please do understand. Questions of these kind are not there in any of the book. I thought, okay, maybe it will help you to analyze even the questions of this rotating one. So any rotating things also will come into picture. This pendulum one is there in SU Verma, what I explained now. Even for rotating disk also. Not only this, even for rotating disk, in anywhere you can bring it. One more last 10 minutes, then we'll finish off this. I'll give one more example. This is not correct. There's a cylinder which is rotating about this axis. Then I will generate here an external magnetic field. It's given angular velocity and release cylinder. And we have an external magnetic field here that is switched on, and that magnetic field, let it be time varying one. Anything will happen to the cylinder, no? This is a metal cylinder. Solid iron cylinder. So the cylinder is given angular velocity omega naught about its axis, and then time varying magnetic field is switched on. Describe the motion of cylinder. Anything will happen to a cylinder? It will undergo retarding torque due to eddy currents. So what is the answer we can write? Due to eddy currents, a retarding torque acts on the cylinder. And hence cylinder rotates with decreasing speed. And finally comes to rest. Afterwards, again, we'll don't know. So decreasing speed, we'll write it. So the retarding torque will be in this direction. This is torque due to eddy currents. Very simple. That eddy current, somebody may bring that eddy current varies with angular velocity or varies that one. Now you go back to the kinematics of circular motion and work out. Don't get scared. Anything here? Oh, we'll end up the class. Yeah. Okay, kids, we had a discussion about the eddy current. I think it's just me. The first topic where I didn't do any numerical. Hope you remember in the total physics. I think any topic I usually work out many numericals. I think the only topic where we don't have numericals here. So that's why I thought of like, better let's give a lot of examples, but many ways they can ask you. Even some of the questions, even I may find difficult, okay, what will happen? Because you have to understand that how eddy currents are there and how that eddy current will impact the motion. I think this will be a very challenging one. So I give some set of good number of examples, almost some 7 examples I give. Anything related to this can appear in any of the exams. You also think on this better. You'll be on safer side, but it's very important topic. Okay, we'll end up the class. After a certain time, we'll meet.